Today we're going to look at the chi-square test of homogeneity of populations. The purpose of this test is to test the null hypothesis that a categorical variable has the same distribution in two or more populations. Now the data are going to generally come to you in the form of a two-way table, and when you look at it, analyze what you're getting. Okay? If you see one categorical variable and two or more populations represented in the table, then this will be the appropriate test, or is likely to be the appropriate test. The conditions are that the data are counts. We have an independent random sample from each population. All the expected counts are greater than or equal to 5, and the sample observations are independent. So these are the same as for the goodness of fit test, except here we have to have an independent random sample from each population instead of just one random sample. The formula for the test statistic is the same. For each cell in your two-way table, you calculate the difference between the observed count and the expected count, square it, divide by the expected count, and then sum up all of those components for every cell in the table, and that gives you your chi-square statistic. The expected counts are calculated a little bit differently in this case compared to the goodness of fit test. You multiply the row total, that's the total at the end of the row that you're calculating that expected count for, times the column total, the total at the bottom of the column that you're calculating the expected count for, and divide by the table total. The degrees of freedom are the number of rows minus 1 times the number of columns minus 1. And you can find this on your calculator at stat test C. It's chi-square test. Let's look at an example of how this works. You'll typically see this test in the context of experiments, clinical trials, etc. Okay? A researcher wants to see if smokers who are trying to quit with the aid of a nicotine patch will be more successful in quitting if they also take an antidepressant drug. 245 subjects go into group 1. They are randomly selected and assigned to receive the patch and the drug, and 244 subjects, group 2, are randomly assigned to receive the patch and a placebo. A subject is considered successful at quitting if the subject has not smoked for a year after beginning treatment. The observed counts of successes and failures are shown in the table below. Do these data provide evidence that success is distributed differently for the two treatments? Well, we have our one variable, success. It has two values, yes and no. And then we have group 1, which comes from one population, and group 2, which comes from another population. And what I did here is I augmented the table and I calculated the row totals over here on the right. 87 plus 40, etc. is 127. And I calculated the column totals down at the bottom. These two column totals add up to 489, as do these two row totals. So that's the way you can check your work. Now I'll talk about the expected counts in a minute. They're based on the null hypothesis that success is distributed the same for the two treatments versus the alternative that success is distributed differently for the two treatments. Now where those expected counts come from is a process of multiplying for each cell the total in that row times the total in that column and dividing by the table total. Okay, so how I got these was for the first row, first column, I multiplied 127 times 245 and divided by 489. I got 63.63. For this expected count, I multiplied 127 times 244 divided by 489, and I got 63.67, etc. And then these expected counts, I got pretty much doing the same thing, only I use different row totals and column totals as needed. Okay, so for every cell, find the row total for that cell and find the column total for that cell and multiply those together and divide by the table total. Now why do we do it that way? Well, it's basically like this. If success is distributed the same for the two groups, then you would expect each group to have a proportion of 127 out of 489 successes. Okay? And then you multiply that proportion times the number of subjects or observations that are in that group right there. So we're going to multiply 127 divided by 489 times 245. And there it is, and that's where we get the 63.63. Now, failure should also appear in the same proportions. And the proportion of failures overall is 362 divided by 489. So for this expected count, we would multiply this number of observations times this proportion, 362 over 489. And that's where that number comes from. And we did that for all 4 cells in the table. But that's based on the null hypothesis. Now, the conditions for this test are the data are counts, and they are by inspection. The treatment groups are randomly assigned, so that takes care of the randomization condition. All the expected counts are at least 63, which is substantially greater than 5. And it's plausible that the observations within the groups are independent. So the conditions are met. When we do this test, we're going to calculate the chi-square statistic. The way to do that is to take the observed count minus the expected count for each cell, square it, divide by the expected count. And I did that for the top row, first column, and top row, second column, and then the other two just follow the same pattern. They all add up to 23.2371. We have degrees of freedom equal to 1. That's 2 rows minus 1 times 2 columns minus 1. 1 minus 1 is 1. The p-value for this test is about 1.43 times 10 to the minus 6. That's very small, so I reject the null hypothesis. I reject the null hypothesis that success has the same distribution in the two treatment groups. I find strong evidence that success is distributed differently. In particular, if you reject the null hypothesis, you should do a follow-up analysis and talk about why these two distributions are different. Okay, the main point about all this is that the rate of success in quitting smoking is substantially greater for subjects who take both the patch and the antidepressant drug. And that's the real takeaway from all of this. It appears that the drug is very effective at helping people to quit smoking, at least in comparison to a placebo. Okay? Now, we could have done this as a 2 proportion z-test instead, where we compare the success rates for the two treatments, P1 and P2. The null hypothesis would be that they're the same, that is, neither treatment is any better than the other, versus the alternative that the success rates are different. It's a two-sided alternative. And if we had done that, we would have obtained a z-statistic of 4.8205 and a p-value of 1.443 times 10 to the minus 6. You notice that p-value is the same as that one. And if you were to square this z-statistic, you would get the value of the chi-square statistic that we got. Okay? So once again, the chi-square statistic is the square of the z-statistic, and the p-values are the same.